Okay, hello and welcome back to another video. So today I'm going to start by deriving the expressions for the overall thermal resistance for heat transfer across materials in series and in parallel. So for materials that are in series, it's going to look like the example that we had a few videos ago. Oh my goodness. Where it looks something like this. So this was air, this was an insulator, this was glass, and then this was coffee. And this was the coffee at some temperature. There was a temperature here for at the surface of the glass, a temperature here for the surface where the insulator and glass are in contact, and a temperature here where the air and insulator were in contact. And then we had the temperature of the air as well. And then remember, we had the heat flow. This was by convection because it was a fluid making contact with the surface. The glass and the insulator were both heat flow through conduction because the two surfaces making contact with each other. And then the air again was making contact with a fluid, so that was convection also. And remember that for conduction, this is Fourier's law. It's negative thermal conductivity times the cross-sectional area, the change in temperature over the change in position. And then this was evaluated from for the length of the glass, and then again for the length of the insulator. And then for convection, that is the height of the surface times the cross-sectional area times the change in temperature. I'll just say delta T. So let me write this all the way out. So we had the heat flux of the coffee is the height of the coffee times the cross-sectional area. Say coffee. And this was times the change in temperature, which is the temperature of the coffee, minus the temperature at T1. And then we had the heat flux of the glass. That's equal to the negative thermal conductivity of the glass times the cross-sectional area times the change in temperature, which was T2 to T1. And then this was over the change in position, which is the length of the glass. This is similar for the insulator. The negative thermal conductivity of the insulator times the cross-sectional area times the change in temperature, which was T3 minus T2. And this is for the length of the insulator. And then for the air, the heat flux of the air was by convection. So you have to do the height of the air times the cross-sectional area. And the change in temperature is going to be T3 minus the temperature of the air. And then remember also that the net heat flow is going to be equal to the heat flow of each of these individual sections. So this is going to be that Q net is equal to all of these. So we can copy all this down. I'm gonna run out of room here. And then it's also equal to the heat flux of the air. So something like that. And then similar to the last video, we want to find the resistance of all of these. Or the thermal resistance, rather. So if we think about resistance, we can think of Ohm's law, which was the change in voltage is equal to the current times the resistance. And if we can imagine what this looks like, this is going to be the voltage at 2 points, that's the change in voltage, and current flows from one point to another. And somewhere in here, there is some type of resistance. Now, if we look at Fourier's law, we have that the heat flux is equal to negative thermal conductivity times the area times the change in temperature over the length, because on all of these we have it's just the length of the glass and the length of the insulator, so we can simplify it that way. And with Fourier's law, we have that there's a temperature at 2 different points, and there's a heat flowing through the points, and then there's some type of resistance, which can be the thermal resistance. So looking at these, we can see there's a change in voltage similar to how there's a change in temperature. So let's relate those two together. And then we have the current is flowing through here, and then we have that the heat is also flowing. So let's relate those two together. And then for Ohm's law, the rest of it is the resistance. So we can say that the rest of this equation is also resistance, or thermal resistance. And this is going to be L over negative thermal conductivity times the area. So that is for that. So this here is what the thermal resistance is by ways of conduction. Let me just write it. Like that. And then now that we have this analogy that the delta V is similar to the delta T and I is similar to Q, we can find the thermal resistance by convection as well. So remember Ohm's law is the change in voltage is the current times the resistance. And then we said that the heat flow for convection is heat flux is equal to the height times the area times the change in temperature. And we already related the change in voltage to the change in temperature. So let's set those equal and say that's equal to the heat flux times 1 over the height times the area. So then this part here is the thermal resistance by convection. And then before I'll rewrite it, we said it was the length over A, and that was resistance by conduction. So remember that with Ohm's law, when you have resistors in series, that you can just add the resistance to get the total resistance for the circuit. So we can apply the same idea to heat flow in series. So remember, we had this up here, this equation. So let's apply that using the resistance that we just found here. So we have that the total resistance so the total thermal resistance is going to be this one, the first one, the coffee, is by convection. So this is going to be 1 over the height of the coffee times the area. And then you're going to add it to the resistance by conduction from the glass. It's going to be the length of the glass over the thermal conductivity of the glass times the area, and then the resistance by conduction again for the insulator is the length of the insulator over the thermal conductivity of the insulator times the area, and then by the resistance by convection of the air is 1 over the height of the air times the area. And then the cross-sectional area is going to be the same for all of these, so you can factor that out. So the thermal resistance is equal to 1 over the area times 1 over the height of the coffee plus the length of the glass over the thermal conductivity of the glass plus the length of the insulator over the thermal conductivity of the insulator plus 1 over the height of the air. And so this is the total resistance. So if we have the total change in temperature is going to be equal to the heat flux times the total resistance. So then for this, we can say this was going to be the total change in temperature is from temperature of the coffee all the way until the temperature of the air is equal to the total heat flux times 1 over the area and then times the total resistance. So that would be this whole section. Like that. And then we can use this more simplified equation to find the total heat flux. We would just have to rewrite it to be that Q is equal to, this is going to, this whole section is going to be divided over, so it's going to be the reciprocal of it. It's going to be 1 over the total resistance times the area times the change in temperature overall. So that's how we can use Ohm's law to find the total thermal resistance in series and the total heat flow in series using the thermal resistance analogy for heat transfer. And now we want to look at thermal resistance in parallel. Okay, let's look at series and parallel. So here's parallel. So for Ohm's law, with resistance in parallel, it is something like this. So there's a resistance here, and a resistance here. This current is I1, and this current is I2. And so this is still the change in voltage is equal to the current times this is total resistance. And then the total current is I1 plus I2. So how this was going to look in heat transfer, let's say that you have a wall. And on the right side of the wall, this is a temperature 1, and then on the left side is temperature 2. And let's say that the top of the wall is made of wood. And the bottom of the wall is made of brick. Like the whole wall is made of brick, but this right here is a wooden stud. So this is going to be, or within this section up here, this is going to have a thermal conductivity of wood, and then there's a thermal conductivity of the brick as well. So going back to Ohm's law over here, we can say that I1 is equal to the change in voltage time or over the resistance of 1. We can say that I2 is going to be the same thing, the change in voltage over the resistance of 2. So this is resistor 1 and resistor 2. This will give us that the total current, let's say total is equal to change in voltage over R1 plus the change in voltage over resistor 2. Okay, so now we can look back at this overall equation and plug in what I is. So that's going to be that the change in voltage is equal to the total resistance times I1 plus I2, which is the total current. That's going to be what we just said. It's the change in voltage over resistor 1 and resistor 2. And we want to find what the total resistance is. So we want to find this. So let's factor out the change in voltage. It's just going to be 1 over resistance 1 plus 1 over resistance 2. So here, these will cancel, and this will be a 1. I'll do this. And we can divide over the total resistance. And then we have this term here. So this is how you find the total resistance for resistors in parallel using Ohm's law. So now we want to try to relate this to thermal resistance in parallel for this example up here. So remember what we said earlier in this video, that thermal resistance by conduction is the length over the thermal conductivity times the area. So the resistance of the wood is going to be the length of the wood over the thermal conductivity of the wood times the area. And then the resistance, the thermal resistance of the brick is the length of the brick over the thermal conductivity of the brick times the area. So similar to what we did over here with Ohm's law, this part here, or rather you want to focus on the total current flow first, because again, what we said earlier, that using the thermal resistance analogy for heat transfer, relating it to Ohm's law, we said that, I'll just write it here, that the change in voltage is going to be similar, we're going to relate it to the change in temperature. And we said that the current is related to the heat flow. And we said that the resistance for in Ohm's law is similar to, we're using the thermal resistance here, right there. So if we focus, if we're trying to find the total heat flow for this example through the wood and the brick, we know that Q total is equal to the heat flux of the wood plus the heat flux of the brick. And this is the exact same thing as right here. That's where we're at. And so then we have here and here that current was equal to the change in voltage over the resistance. So we can say that, let's do this, that the heat flow through the wood is equal to the change in temperature over the thermal resistance of the wood. So let's just rewrite it. Oops. This is going to be, oops. The thermal conductivity of the wood times the area over the length of the wood. And we're doing the same thing for the brick. The heat flow through the brick is equal to the change in temperature times the thermal conductivity of the brick times the area over the length of the brick. And then we can put all this information together by plugging it into here, just like we did when we found the total resistance or the total current using Ohm's law. So let's do that. So total heat flow is change in temperature times negative thermal conductivity of the wood times the area over the length of the wood. And this is added to the change in temperature times the thermal conductivity of the brick times the area over the length of the brick. Like that. And then now we want to plug this into the overall equation. So how we plugged in this right here, we're going to do the same thing but for heat flow. So we know from earlier that, let me make a new page. We know that the change in temperature, the total change in temperature, is equal to the total thermal resistance. Now this is total times the total heat flow. So we just said this is, I'll just say that the T is thermal. We just said that the total heat flow is this right here. So let's copy that down. Like that. Okay. And then looking at this, if we factored out the change in time, or rather change in temperature, sorry, this would all cancel. This would be a 1. And we divide the total thermal resistance over. And we are left with this, where this is still thermal conductivity of the wood times the area over the length of the wood plus thermal conductivity of the brick times the area over the length of the brick. And really, this is 1 over R and 1 over resistance 2. Because if we look back, initially the length was on top and the thermal conductivity in the area was on the bottom. And now it's the opposite, which is just like this here. So that's how we can use Ohm's law and the thermal resistance analogy for heat flow and resistance in parallel. So now let's look at an example where we can apply both of these ideas. So let's look at this example. So we have a wall. Say it looks like this. And along this wall, we have a window. Let me make this a little bit longer. Okay, so this is going to be glass. Take glass 1, this can be glass 2. This over here is going to be outside. So let's say that this is air. We'll be going this way. And this can be the inside. And then we have a stud. And let's make this side bigger as well. And then up here, we have brick and insulation. So the brick is on the outside, and the insulation is on the inside. Okay, and we can say, let's just say that it's hotter outside than it is inside. So the temperature is going to be changing in this direction. So remember from earlier, we said that the net heat flow is going to be equal to the heat flow of each of these individual parts. So let's look at the one in series first. Let's look up here. So this first part is going to be from the inside air to the insulator. This is going to be the heat flow by convection. And this can be inside. And then, or rather this would be an equal sign because it's all equal. And then we have the heat flow from the insulator to the brick. So this is going to be heat flow by conduction of the insulator. And that's equal to this heat flow from the brick or through the brick rather, just still conduction. And that is going to be equal to this heat flow to the air, which is convection again, like that. So that was the net heat flow up here through the wall. So let's say this is wall. Okay, and then we want to do the same thing for the heat flow through the stud, because this is still in parallel for that part, or rather in series, I mean. So then the net heat flow through the stud is the same thing, the heat flow of convection from the inside is equal to the heat flow by conduction, but this time from the stud. And that's equal to the heat flow of convection through the air. And we also need to know the net heat flow through the glass. This is going to be, again, the heat flow of convection from the inside is equal to the heat flow by conduction from glass 1, equal to the heat flow of conduction through glass 2, and that's equal to the heat flow of convection through the air. So this is how we get this whole thing simplified into just 3 main heat flows. And then remember from what we derived earlier in the video that the thermal resistance from conduction was going to be the length over the thermal conductivity over the area. And we said that the thermal resistance based on convection was 1 over the height times the area. So if we want to find the total resistance in series of each of these, we just add those all up. So for the resistance, the total resistance from the wall in series is going to be convection from the inside, which we said was 1 over the height times the area of the inside, plus the resistance from conduction from the insulator, which is the length of the insulator, over the thermal conductivity of the insulator times the area, plus the conductivity of the brick. So this is the resistance by conductivity of the brick, plus the total resistance, or the resistance of convection from the air. So this is the total resistance of the wall of it in parallel. And then we can do that for each of these. So then we have the resistance from the stud. And this is in parallel, was from convection 1 over the height of the inside. This can just be in for inside, plus the conductivity of the stud, this is the length of the stud, over thermal conductivity of the stud times the area, plus 1 over the height of the air times the area. And then the same thing for the glass panes. The convection of the inside resistance is the height of the inside times the area plus the length of glass 1 over thermal conductivity of glass times the area plus the length of glass 2 times the thermal conductivity of the glass times the area plus 1 over the height of the air times the area. So this is what we're getting in series as we're going across here. That's what I said before. So let's just draw a new picture just because we can. So this is what we're looking at right now. There's a temperature inside, there's a temperature outside. And then we have the resistance here. This is wall. This is the resistance of the stud. And this is the resistance of the glass. This is total. So now these are in parallel. So we said from earlier that to find the total resistance in parallel, we have this equation, and we derived that from Ohm's law. It was 1 over the total resistance is equal to 1 over R1 plus 1 over R2. And you're just doing 1 over the resistance to get to the total. So let's do that. So this is going to look like the total thermal resistance is in the denominator, and you're going to be adding the resistance of the wall, or 1 over the resistance of the wall, plus 1 over the resistance of the stud, plus 1 over the resistance of the glass. So if you plug in all of this information there, and there, you can get the total thermal resistance of this entire system here, this whole thing. And then you can manipulate the equation around to get the total net heat flow through the entire system using the thermal resistance analogy from earlier in this video. That's how we can apply it to something more complicated in this example.